Hi everyone, Professor Bob Young here. In this instructional video, we're going to look at some right triangle trigonometry and solve some problems involving navigation, bearings, and for some physics problems, just for good measure, we'll do some simple harmonic motion problems. So again, the thing I love about trigonometry, you can use it in so many real-life applications, and we're going to get back to the famous Indian chief, Sakatoa. So get ready. All right, so solving a right triangle means finding the missing links of its side and the measurements of its angles. We will label right triangle so that side A is opposite angle A, side B is opposite angle B, and side C, the hypotenuse, is opposite right angle C. So remember, the hypotenuse or long side of the right triangle is always opposite the right angle. And when solving these right triangles, as I said earlier, we will use Sakatoa, sine, cosine, and tangent functions rather than their reciprocals. All right, so let's take an example here. We're going to let angle A be 62.7 degrees and side A equal 8.4. Solve the right triangle, rounding lengths to 2 decimal places. All right, so what we need to see here is angle A plus angle B will add up to be 90 degrees. So if you have a right angle C here, these other two angles are going to be complementary angles and add up to 90. So all we have to do to get angle B is go ahead and subtract 90 minus 62.7. There's the first piece of our puzzle, 27.3 degrees. All right, so let me go ahead and put that in here. So we've got 62.7 degrees for angle A. For angle B, we just found 27.3 degrees. And now we can go ahead and attack this thing a whole bunch of different ways to find the other pieces of the puzzle here. Now remember, we were also given that side A is 8.4. So let's look and have some fun here with things we've talked about earlier with right triangle trigonometry. If we looked at trying to get side B here, let's go after it, all right? Let's think about what we would do if we were going to relate angle A and side B with all the rest of the stuff we're given. What you need to see here, and there's a couple ways you could attack this. You could say the tangent of 62.7 degrees equals the opposite side, 8.4, divided by the adjacent side, B. So remember, tangent means opposite over adjacent. Or if you use this 27.3 degree angle, you may say something else. You may say, well, the tangent of 27.3 degrees equals, what's opposite of this angle? B over here would be B over adjacent 8.4. All right, so there's a whole bunch of ways that you can solve these things. Which of these two equations, looks a little bit easier to solve? Well, either one you could do, but if you multiply this right one by 8.4, B is going to equal 8.4 times the tangent of 27.3 degrees. And we'll go ahead and approximate that 2 decimal places. It says, now I want you to go ahead and get your calculators out, get it in degree mode, and I want to make sure we agree on these answers. So do that, and I'm going to hit pause real quick and get my calculator. All right, I'm back, and when I hit 8.4 times the tangent of 27.3 degrees in degree mode, I got about, let's see here, 4.34 for the length of side B here, 4.34. Now you can tell this picture is not to scale here, obviously, because this 8.4 should be much larger than this, and that happens in a lot of trigonometry problems, so don't worry about that. Now also, if we were going to do it using the 62.7, we would have multiplied both sides by B and said B times the tangent of 62.7 degrees equals 8.4, and then we would divide both sides by 62.7 degrees, the tangent, of 62.7 degrees. So let's do that real quick. And gee, it comes out 4.34 again. Isn't that a wonderful thing? All right, now there's a whole bunch of ways we could get side C based on this. I mean, we could use the Pythagorean theorem for right triangles, say a squared plus b squared is c squared, or we could use SOHCAHTOA with either of these two angles. I think I'm going to go ahead and say the sine, just to show off here, of 62.7 degrees is going to equal the opposite 8.4 over the hypotenuse c to get c. All right, you could do it that way. And then multiply both sides by c. You'll get c times the sine of 62.7 degrees equals 8.4. Divide both sides by the sine of 62.7 degrees. And c will be approximately, and it better be longer than a and b, so make sure you make a note of that as well, or we're really in trouble if the hypotenuse isn't the longest side, is about 9.45 rounded two places. So that would do it. All right, so there is an example of given certain parts of a right triangle. If you're given an angle and a side, you can pretty much get everything else. All right, let's take another example here, a real world problem. From a point on level ground 80 feet from the base of the Eiffel Tower, beautiful drawing there, much better than some of mine on the board in my lecture classes. The angle of elevation is 85.4 degrees. Okay, now the angle of elevation is like if you were standing on the ground and looking up and seeing the top of something, all right? And we'll talk about that in a little bit. Approximate the height of the Eiffel Tower to the nearest foot. All right, so here is us down here looking up at the top of the Eiffel Tower here, okay? So this angle right here is the angle of elevation, and if there was someone up top here looking down, this angle right here would be called the angle of depression. So angle of elevation, angle of depression. It's not a sad angle just because it's depressed. And also notice that these two angles would be congruent. If you all remember your old high school geometry, if you have two parallel lines cut by a transversal, I don't know if you all remember your old high school geometry, but those would be called alternate interior angles. All right, so to find this missing side now, what we're going to do is say either sine, cosine, or tangent here. So if you look at this 85.4 degree angle, A would be opposite, 80 would be adjacent, so we don't have to really worry about the hypotenuse on this one. So which one of those, SOHCAHTOA, sine, cosine, or tangent, would y'all say to use? I hope you're picking tangent. 85.4 equals opposite over adjacent here. All right, now to solve, multiply both sides by 80, put that in your calculator, and hopefully you're going to get about 994 feet for the height of the Eiffel Tower to the nearest foot. Okay, let's look at another problem here. We've got a guy wire is 13.8 yards long and is attached from the ground to a pole 6.7 yards above the ground. Find the angle to the nearest tenth of a degree that the wire makes with the ground. So let's first go ahead and sketch a picture here. And you might want to try this on your own here, put it on pause, and then I'll come back and I'll have a picture. All right, so do that. All right, here we go back here. So here is a picture here. So here's the pole. And y'all know that guy wires kind of are those long wires that kind of keep the pole from embracing the pole and so forth, and maybe during hurricanes it won't fall over and everything. So we've got the guy wire measuring 13.8 yards long. The pole is 6.7. All right, so now to find this angle here, there was only some way we could find an angle. Some lesson we had talked about to find an angle. Oh yes, the angle getter. We can use either arc sine, arc cosine, or arc tangent to get this angle. The angle getter, if we know which one to use, and since we're given this side looks to me to be the opposite, and this is the hypotenuse given, I'm going to go ahead and take a long shot here and say the sine of A is going to be opposite divided by hypotenuse. All right, so to get this angle, To undo sine, we're going to go ahead and take the inverse or arc sine of both sides of the equation. So that will give us a, and if you go ahead and round this to the nearest tenth, let's pause and do it on your calculators, make sure we're getting the same answers. Right, I came up with about 29.045, so if it says to the nearest tenth, that's just going to be 29 degrees. All right, so that's what you should have got. Continuing, we're next going to look at trigonometry and some bearings here. Now, in navigation and surveying problems, the term bearing is used to specify the location of one point relative to another. The bearing from O to point P is the acute angle measured in degrees between ray OP and a north-south line. The north-south line and the east-west line intersect at right angles. Each bearing has three parts, a letter N or S and a measure of an acute angle, and a letter E or W for east or west. So let's go ahead and look at a few of these, and we're going to sketch the figure. So if they want you to find south 45 degrees west, and of course we know on our standard compasses here, this would be north, south, east, and west. So we're going to do some navigation and bearing problems. We would go south 45 degrees west here. So we would split this right angle, and this is the angle we're in question here, south 45 degrees west. So they might call this initial point here O, and down here P for ray OP. That would form this angle in navigation. All right, let's try a few more. North 70 degrees east, we'd be heading this northerly direction, and then from the easterly, we're going to go 70 degrees. So this would be a wider angle in here, and this would be the angle in question, ray OP. All right, south 15 degrees east, we would go south and then a 15 degree, kind of a thin ray here, OP. And my writing tablet gets a little slippery, so forgive me if these aren't perfect lines and so forth, but I think you're getting the gist. Now, wait a minute here. I don't see any directions on these young. Sometimes in the old West, when they were doing navigation, they always went by the North Star. So if they don't give you a north, south, east, or westerly direction on some of these, it's from true north. And so 100 degrees from true north, and y'all aren't going to like this because you're going to have to go a clockwise direction from true north. So going from the northerly direction here would be 90 degrees. So we'd have to go another 10 degrees, which would just be kind of a sliver there. So that would be the angle in question. And I must warn you, sometimes they give you things like this, and sometimes like over here, you may be looking at this angle, or you may be looking at this angle. So be careful in application problems. And I know some of you go, but Young, if it's a positive angle, it goes counterclockwise. Not in navigation and bearings, I'm sorry. Now, where would 240 be? Let's start at true north again. 90, 180, 270, that's too far. We got to back up 30 degrees. So it would be from true north. This is the angle here, 240 degrees from true north. All right, so we'll just do a few more examples to make sure you've got them here. So the bearing from O to P here is going to be north 40 degrees east. That's what that one would look like. So we'll do several more examples. The bearing from O to P here, north 65 degrees west, would look like this. And we're going to give you all a few to try here in a second. After we give you one more look here, south 70 degrees east, because you may see these in lots of word problems and so forth. Be careful. Are you ready? Let's try one ourselves. Think about this one, the bearing from O to D right here. So here's the picture. Instructors love to put these type problems on the test. Think about it a second. Now, point D is located to the south and to the east of the north-south line. So the bearing from O to D, did y'all get this one, is south 25 degrees east. All right, now think about this one. I'm going to pause for a second, and you can pause too. The bearing from O to C, be careful here. Be very careful. All right, what do you think? How about south 15 degrees west? Again, I told y'all to be careful. Sometimes they give you this piece and it's really this piece you need to get the bearing. So beware. All right, last part of this video, we're going to talk about some simple harmonic motion. And these two formulas may look kind of um, familiar from past lessons. Now, in physics, it says an object that moves on a coordinate axis is in simple harmonic motion if its distance from the origin d at a time t is given by either one of these two creatures, d equals a cosine wt or a sine wt. And man, if you remember your sine and cosine graphing, you might remember some stuff here. So look at this. The motion has an amplitude A, the maximum displacement of the objects from its rest motion. So now this is going to be A is the maximum displacement here, the amplitude. Notice it's going to be positive with that absolute value. The period here is going to be 2 pi over W. Remember when we graph sines and cosines, that was a B there, but that's all right, where W has got to be greater than 0. The period gives the time it takes for the motion to go through one complete cycle. All right, in describing simple harmonic motion, the equation with the cosine function d equals a cosine wt is used if the object is at its greatest distance from rest position, the origin, at time t equals 0. By contrast, the equation with the sine function d equals a sine wt is used if the object is at its rest position, the origin, or at t equals 0. So remember, the basic sine function went through the origin, and the basic cosine function started at 0, 1, or off the origin. So that's something to keep in consideration as we look at some of these. So a ball on a spring, here's the first example here, is pulled 6 inches below its rest position and then released. The period for the motion is 4 seconds. Write the equation for the ball's simple harmonic motion. All right, so when the ball is released, t equals 0, the ball's distance from its rest position is 6 inches down. Because it is down, d is negative. All right, so we're going to say when t is 0, d is negative 6. The greatest distance from its rest position occurs at t equals 0. That's where we're going to use cosine in this case. A is going to be the maximum displacement. Because the ball is initially below rest position, A is going to be negative 6 in this one. The value of W can be found using the formula for the period, which we said was 2 pi over W. So we can say 2 pi over W is 4, since they gave us the period as 4 there. So multiplying both sides by W, we're going to get 4W equals 2 pi. Divide by 4, W is going to be pi over 2. So now we can say the equation for this d is going to be negative 6 cosine pi over 2t. Now, I know I said the amplitude was always positive, but in these questions here, you have to be careful on how that problem is worded as well here. I mean, if we were just after the amplitude in the normal problem, we would say it's positive 6. But this one, again, it's pulled 6 inches below its rest position, so be careful. All right, so an object in simple harmonic motion given by d equals a cosine wt or d equals a sine wt also has a frequency that's given by this, f equals w over 2 pi, or I think we've said that's omega, the Greek letter w, omega there, where omega is greater than 0. And it's kind of the reciprocal of the period, the frequency. So notice here it says the frequency is 1 over the period, or you can take the reciprocal there of the period. So let's go ahead and we'll look at this one again here, or one more. It says an object moves in simple harmonic motion is described, so they give us the equation here, 12 cosine pi over 4t, where t is measured in seconds and d in centimeters. It says find the maximum displacement. Now remember we said that was the A part of it here. So the maximum displacement from the rest position is the amplitude, because A equals 12, the maximum displacement is 12 centimeters. An object moves in simple harmonic motion described by this. We want to find the frequency next. So the frequency is W, or omega, over 2 pi. And you all know what omega here is. In this one, it's going to be pi over 4 over 2 pi, which we have to multiply. Since we're dividing fractions here, we have to multiply by the reciprocal 1 over 2 pi. And the pi's out, and you will have 1/8 is the frequency here. So 1/8 cycles per second. All right, so finishing up here, it says find the time required for one cycle here. So the time required for one cycle is the period. So we're going to say the period is 2 pi over W. Now we just found the frequency, so we could just go ahead and take the reciprocal of 1/8 there and say it's 8. But they just went ahead and they showed you could take 2 pi over omega and the relationship between the frequency and period there, as you see. All right, so with that, we're going to go ahead and conclude this video, applications of right triangles, and we will move on to some new and exciting lessons as we continue.